So I think we can start. Welcome to the third webinar organized by the EVACES Association. I'm Pier Francesco Giordano, and now I'm an assistant professor at Politecnico di Milano in Italy. And today I will be the moderator for this webinar. Before introducing today's speaker, I would like to take a moment to briefly present the EVACES Association. Can you see my screen?
Yep.
Yes. Perfect. So the International Association for Experimental Radiation Analysis for Civil Engineering Structure was established in 2023 following the last EVACES conference held in Milan. The association serves as a platform for researchers and professionals working in the field of experimental vibration analysis applied to civil engineering structures. And the aims of EVACES go beyond promoting the biennial international conference. Our mission is also to foster collaboration between academia and industry, support dissemination activities, and also recognize excellence throughout awards for outstanding scientific contributions. Here you can see the current board of the EVACES Association. We have Professor Maria Pina Limongelli, who is the president of EVACES, and she was the chair of the last conference in Milan. Then we have Professor Alvaro Cunha from Portugal, who is the chair of the upcoming conference in Porto this year. Then we have Professor Rodrigo Astroza from Chile and Professor Jidang from Japan, who serves as chairs of previous edition of the EVACES conference. And then there is myself. I serve in the scientific secretariat of the conference in Milan, and currently I coordinate dissemination activities and promotion of the association in general. Here you can see that we have a website where you can find all the relevant information about the association and our initiatives, and you can get you can access the website throughout the QR code that is shown in the slide. And we also invite you to follow our LinkedIn page, which is always updated, and we use it to share events and news. And recently, we also opened a brand new channel on YouTube channel where we collect the recordings of our previous webinars, and this is a growing resource for anyone that is interested in the latest development in this field. And again, you have the QR code if you want to check this website. So a few words about EVACES, the conference. The first conference was in Bordeaux, in France, in 2005, and since then it has been held every 2 years in various locations around the world, as you can see in this list. The most recent edition was in Milan in 2023. As we said, the chair was Professor Limongelli, but also there were other people involved that are Professor Carmelo Gentile, Professor Marco Belloli, and Professor Alfredo Cigada, all from Politecnico di Milano. And this conference was quite successful, and there were 229 participants from several countries. We managed to cover all the continents. We had 25 special sessions, and also we were able to collect 157 papers in the conference proceedings, which are published by Springer. A selection of these papers was also was further developed, and we published a special issue on the Journal of Civil Structural Health Monitoring that has been just published last month. The next conference will be in Porto, Portugal, this coming July, and will be chaired, as we said, by Professor Alvaro Cunha, but also by Professor Elsa Caetano. So far, we have reached over 300 papers submission, and we look forward for this for another outstanding event. Here you have the QR code that will direct you to the conference website for more information. Here you see the long list of the member of the scientific committee, which represent diverse areas of expertise and geographic regions. And also we have an industrial committee that underscores strong link between academia and industry. That is one of the core values of our community. And as you know very well, among the recent initiative, we also have started this webinar series featuring international experts presenting the latest advances in the experimental vibration analysis of civil structure. And today we are honored to host Professor Helmut Wenzel, who is the Managing Director of WENZEL Consulting Engineering. And Professor Wenzel, you know him very well, I guess, has been deeply involved in bridge engineering, construction, structural monitoring throughout his long career. His contributions span major infrastructure projects, and where his expertise design, construction technology, and asset management has played a very important role. And also, he was a technical advisor for many large-scale projects all around the world. He was the developer of BRIMOS, which is a widely recognized bridge monitoring system. And under his leadership, VCE, at VCE, more than 6,000, that's an impressive number, of bridges have been monitored since 1995. And today, Professor Wenzel will deliver a presentation, which is titled Successful Vibration-Based System Identification of Bridges and Offshore Assets. The presentation will be more or less 40 minutes. It will last more or less 40 minutes. And please feel free to submit your questions at any time in the question and answer box. It's somewhere in the Zoom platform. And now I am pleased to hand over the floor to Professor Wenzel.
Okay. So, hello, good afternoon, everybody. Okay, I hope you can see now what the first page of the presentation. I have presented it already in the Milano conference 2 years ago, but have updated a little bit. Vibration-based analysis or assessment has a long history. Already in the 1850s, as far as I understand, some theoretical physicists were aware of the information that you can get from vibrations and specifically ambient vibrations. So what I want to show you today is a short introduction, very, very short, because I guess you know that. And I will have a word on available standards because this is important for practice, and then go through examples. And I will talk about it during we see the slides. I'm looking forward to questions on that. The principle is very simple. The basic idea is if you have a bell, or if you don't want the bell, you can have a wine glass. If you impact it, you will get a sound back if it is a glass or a bell, but you can get vibrations which are in a linear spectrum, more or less, very, very good and clear spectrum. And if it has a damage, then you see it in the spectrum you compute from your records. The rest is seen in many publications, and you can read about this very carefully. We distinguish between key performance indicators, and there are only a few that are really important for us. One is the loss of stiffness, which is expressed by the reduction of the frequency. Another one is a loss of amplitude, which is more or less driven by damping. And if you can look here, you see out of that you can read a lot of things. And then you have the harmonics and all the related information with that. I don't go into details of that. It will be more important to talk about some examples. We did a lot of very good experiments more or less all over the world. This is one experiment from Stuttgart, where a pipeline used in a nuclear power plant has been excited and vibrated until it died, more or less. And what you can see here is the end of life of this pipe. And on the left side, you see the frequencies when there is no damage, and then it starts to develop damage. You have a cascade 5, means this is in the 5th mode. And later on in the 19th mode, you can see heavy excitation. So this is the indicator that there is something wrong. You can find all this thing in the publications about the IRIS project. What is important is, first of all, we have to know the physics behind it and understand science. But later on, to sell it, it is important that we have something to give to the clients, potential clients, to show that these methodologies are already well developed. And we were able also, as one of the product of the IRIS project, to bring the methodology into this Eurocode. Eurocode 16991 went into force in 2018. And you can see if you monitor a structure, then if your record is straight like this, you are here. If your record diverts like this, it is here. These are the records from the example I've shown you before. So this is only the proof of concept. But if anybody asks you, which code are you following? Yeah, you can quote this code. This is very helpful for selling these things. Then a few key projects where we have tested structures where we knew that there are damages. So you can see the corroded post-tension cables, and here's a number of wires involved, and so on. This was a destructive test, but here in 2002 already we were able to show that even if you don't see anything, you put your sensors on the plane structure, you can find where these places are due to the indicators, as we can show in this line. Still very difficult to convince the client about it. And then came the S101 test in 2008 in the IRIS project. This is a bridge which was constructed in the 1960s and had to be replaced because of loading issues and other issues. A frame, three-span frame, and this was a rare case where an owner allowed us to damage this structure artificially. And in this campaign, we got wonderful records about damages. For example, cut off post-tension cable, cut off a pier here and lower it and push it up and such things. And all these cases are very well documented. You can still ask for this data. There are about 1,000 requests already have been done. Since then, we are still offering that free of charge to everybody. And this is more or less the record we received. This is the structure in good condition. This is the structure with the damage of 1 pier. And this is a structure where we cut cable by cable until it failed. So you can have exactly these data you have here. You just let me know, and we will open it to you. Now to examples or to things which might not work. This is a project in India where I have been involved in the cable state construction here, and these are the access bridges, both sides. And what you can see here, if you look closely, is that the bridge should not deform like this. You can see a heavy lifter equipment in the beginning, and this is not a real case where ambient vibration would help you, but at least monitoring, a proper monitoring would help that you do not have a kind of deflection here. of about 1 meter at 145 meter span. And on the other side, if you look to this project, you see that you know, the ring here, as you see here, this is the foundation, and the pier should be in the middle of the foundation, and it isn't. I know it's difficult to make foundations in the middle of a wide river, but if you have this, you know, this weakens your structure. So what happened there was this. The structure was not instrumented at that time. It was early morning. There was nobody in the structure. Nobody heard. One lesson learned was just that, you know, most of these cases happen in the early morning because the stress from temperature differences on the structure itself is higher than anything else. So these are the good news. But you know, what we have learned is that things like this are very well hidden, and the lessons are not learned, and there is no monitoring system to really show deflections which should be there. Of course, in the specifications you can find it, but it is rarely done. A good example, this is one I have already shown from in the last conference, but this is a very good example. This is Osman Ghazi Bridge, main span 1,550 meters. At that time, fourth longest suspension bridge in the world. And I have been involved there from the beginning. And we had this event. If you look here, you know, the main cable, you can see this is a zoom, more or less. The deflection you can see here is about 6 meters up and down. This is the wind record. We had 20 meters per second, not a storm, still traffic on the structure. And people wanted to know it is, you know, this is the bridge and this is the wind. You know, the wind coming about 30 to 45 degrees from the side is the worst case for structures like that. We have a wonderful monitoring system on there, 460 channels, and these are the records of that. So the record of acceleration, this is an acceleration record, is not very high. It was about 0.15 g, not very much. And in terms of, well, this was a record of the pylon, showing us that the bridge is not only vibrating vertically, but also the pylon is participating. It gets very, very complicated to analyze that. And these are the records we get, the raw records, almost nothing to see there. So what happened there was that we came to analyze the structure and find out what the real behavior of the structure is under, let's say, almost normal conditions. You know, 20 meters per second is still good for traffic, and this is of concern. So what helped here was ambient vibration, a monitoring campaign. This you can see here, a typical kinemetrics sensor on the cable itself to find out what the frequencies of the structures are. We did this in several places. This is from the video, also the monitoring at midspan, and we received this interesting well, the dominated frequencies, and this is after some filters, of course, but you can see that the frequency is 0.09 hertz, which is not what should be the mode 1, but it is mode 11. Mode 11 theoretically was one where there is deck and pylon vibration collaborating. This was interesting on one side because it is not exactly clear why the difference is between the theoretical calculations and the real behavior of the structure. This would be a very interesting, even a PhD work, to find out the details on that. Our main findings from our ambient vibration monitoring campaigns is that there's almost in all the cases we have a major difference between design and reality. But normally it is on the safe side, so that the structure is behaving better and not worse. What happened at that time was this is inside the pylon, the huge structure. You can see the elevator, and the only damage the bridge suffered from this event was that the counterweight of the elevator. You know, the pylon is 250-meter high, so this is a real big elevator. It was pulled out of the guides, and it destroyed some of the structures by it worked like a pendulum because of the pylon action. This was the record of a seismic event on the same bridge in the year 2021, and this is the response of the foundation. What you can see here is 0.05, maybe 0.08 meters per second. Very small excitation, and there was no record from the structural health monitoring system on the pylons or on the deck offset. This was a little bit surprising, and we also had to look into this thing. But what we found was, you know, it is always interesting in the big bridges that you do not only do ambient vibration, but you also put some displacement sensors, and particularly where you have expansion joints. And this one recorded after this small earthquake at the permanent displacement. You know, one side was the main bridge and the other side was the access bridge. It is not critical if you look at the values, but at least you can identify weak points from that. So this is very helpful. And here we have an extremely good client who is aware of things that you know, you cannot judge just by looking into books, but where you need some monitoring, and you have to analyze it, and then you can conclude on the consequences of events. And this, I guess, I have shown already also last time, because this is an extremely interesting example. This is the Comoran Bridge in Turkey. This is Eastern Turkey. We have done the design and also some monitoring here and installed a permanent monitoring system. The cantilever from here to the abutment here is at 380 meters. So if you have, you know, a symmetric bridge, this would be 760 meter span. This is a real big span. And you can see the old bridge in the background. It's a very nice photo. And there was there were two earthquakes, actually, of about 7.2 and 7.4 magnitude on 6th of February 2023. This was 7.5 with this epicenter here, and the bridge is here, close to Malatya, about 150 kilometers away. And well, you know, the 40,000 people died in this terrible earthquake event. This is a look at the monitoring system we have installed there. So usually it is very helpful to have you know, in a first stage of monitoring, if the bridge is new and there is no doubt, you should not have a too big monitoring system. And actually, the most accurate, the most interesting information you get from ambient vibration monitoring, you know, where you have accelerometers and a few others. Of course, you need temperature, you need the wind, and all the other things from the weather around it. And it is always advisable to have some displacement sensors where there is a movement between the structures. And this is the record of this event. It is in one regard interesting if you look at that. You know, from here, no, sorry, from here to here, it is 2 minutes. So this earthquake, you know, almost the main shock was almost 2 minutes long, and the whole thing more than 3 minutes. So this is a very, very long earthquake. And therefore, the major damage to all the structures, particularly those with the higher frequencies. So these are all the sensors that are installed there. And the excitation to the structure, this is a record from the nearest seismic station, and the maximum was 3G. So you can see this record. This was the start of not the full record. There was another record after that, but this is the most interesting. So 3G is something we have not seen before on the structures. Anyhow, it is obvious and also clearly understandable why bridges with long spans are not so vulnerable, and that if you have damage, then it is the smaller bridges. Then we had to look at the deck. What did the deck do? So this is this sensor here. X means this is a longitudinal channel, and you have in longitudinal direction of the structure, which is clear when you look at where the epicenter was, that the X direction will be the main excited 1.1 G. This is by far much more than the design spectrum, the seismic design spectrum was demanding. Anyhow, there was no damage to the structure, and nothing we really had to do or change. This was the first one was the main span. The main span is a steel structure. The side span is a concrete structure. You know, it's an asymmetric cable stayed bridge. To balance it, you have to be more heavy in the side span, and in the side span there was still 0.8 G in this huge concrete block was found there, and also it is sitting on bearings, and these are seismic bearings which are able to carry that, and also the bearings are not were not damaged. Nothing had to be exchanged. On the main span deck, Y is a vertical acceleration, and the vertical acceleration maximum was 1.3 G, which is also you know, much more than the code was demanding. And the bridge end is sitting on spherical bearings, and also these bearings were not damaged. Even so, we have to think that the structure must have been lifted by that. But this was not the reaction of the seismic shock itself, but it was more on related to the cable vibrations we have seen there. In the cables, this was a cable close to 0.1119. In X direction, so this means in longitudinal direction, had an acceleration of 2.1 G. And you can see that there are a lot of harmonics going up and down. So we have good damping, but it is more or less running with this earthquake. And this could also be seen on the pylon top. This is a pylon top in cross direction. You can see that the pylon top was vibrating, vibrates, it dies down, it comes again. And this is, the cables are arranged in a hub arrangement. And these cables are up to 500 meters long. And they tend to vibrate for more than 1 hour. And always try to get some maximum of acceleration, and then damping is going to be starting and damps it down. A very, very interesting record, this one. So how is that done? This is a typical Primus recorder on these cables. Normally it's very simple to place some sensor on the cable itself. If you want to have the cable modes also, then you need 2 sensors. And this is applied to about almost 10,000 cables so far. Very reliable, very easy, and very quick to be applied. So you can find out a lot of things by that. This example I also have showed before. I just only give a short introduction. This is Godavari Bridge in India and in Rajahmundry. This is southern India. This is a chain of 28 arches with 100 meter span each. So we have 670 something of these vertical hangers. The hangers are damaged, and some of them have lost their support. So here, this is what has been done. The monitoring work can be done by local people. It's very easy to put clamp a sensor here, and within 1 minute you get a record that shows you whether this hanger is working, what the force is, and what the condition is. You can see here that the condition, inside of the sheath tube is not perfect. And here, just to give you an idea, this is what a very good cable looks like. And the next one is, this is what a failed cable looks like. So here we have a case where even AI could come into the picture and recognize that there is a major difference. And for the other things, unfortunately, in these cases where there are so many parameters involved, AI is normally not very helpful to find out what is really wrong. And cases like this, you rarely have. In these vertical hangers, it happened that one of the hangers almost lost all of the of the wires. So this has been very simple. And normally we make out of that a kind of risk matrix, and show the client, where are the damaged cables and in which sequence to repair it in order to avoid any problems during this repair work. A few other applications for cable monitoring is this one. If you have complicated construction stages where your hanger forces or the cable forces are changing all the time with every construction stage and with temperature and whatever, this kind of thing is extremely helpful. In this project, we just left to the contractor 2 of them, this monitoring, the Primus monitoring systems, and they permanently have sent data to see whether the construction finally achieves what the theory wanted to know. So extreme good application. This was a cold weather project. Here is a hot weather project. This is in Aswan in Egypt. You can imagine, I guess, that this truck does not have the usual 38 tons it should have, but it has about 120 tons on deck. And it was interesting to see how the bridge is reacting. But a big cable stayed bridge like this, is not really harmed. What is harmed here is, of course, the asphalt layer, and the deck itself gets stresses, which is not made for. So also an interesting application and very simple to do. This is a one-day campaign. We also looked into structures, heritage structures. This is the Brooklyn Bridge in New York. And this bridge is very sustainable because it is a well designed combination of suspension and stay cables. Of course, this is very costly because you do two systems on one bridge and a lot of hangers. But also here you can very quick within 1 minute you know what the individual cable forces is. The main problem is to keep all these records in a way that you know later on where it was. This is why the Primus recorder, for example, has a GPS to know where the position of the cables was. It shows that this bridge is a fantastic concept. Another interesting job was one of the twin bridges they have built in China. These are, suspension bridges. A twin suspension bridge is very difficult to analyze in terms of displacements and behavior under certain loads. And the job here was to see how close the theory is to the monitoring results. In the end, it was closer than expected here. This was a little bit surprising, but I think our monitoring campaign here took place at a stage which is not too representative. So it would be interesting to know what a permanent system, if there is a permanent system there, produced. And then this is the third Bosporus bridge in Turkey. This is again a combination of suspension and cable stayed bridge. So similar to the Brooklyn Bridge, not the same, but of course, but similar. And for that one, we were able to first of all monitor the construction of the pylon because 320-meter high pylons are rare. This is a concrete pylon in an earthquake-prone zone. There is earthquake risk. The bridge should be used later on by a railway. It's not yet installed, and the suspension cables should mainly take care of this additional loads. It was a very good application of optimizing what is the minimum, because on new bridges, on new bridges, you're not looking for the smallest detail. You're just looking for the general performance, and if you have the global performance without any doubts, it is not necessary to have thousands of sensors. Here we finally came to 78 channels necessary, which are in the majority vibration sensors. On the pylon, of course, inclinometers and the necessary temperatures and weather station. So this is sufficient. But it also can, the method can be applied to external cables, post-tension cables, and whatever it is, and works very, very reliable. I won't say that there's nothing to do or to develop here, but it is quite mature. And then at the end of the examples, a lot of these lessons we have learned has been introduced in this VDI. This is Verein Deutscher Ingenieure. This is a code of German engineers, and it is a framework for monitoring and assessment of offshore wind assets. The interesting case in offshore is that half of the year you cannot visit them, you cannot inspect it properly. So people said, you have to monitor these structures. And this is a guideline that also says why and also says how. What do you do? Because these are all new structures. So we are not looking for the typical damages that occur in old structures, but we have the possibility to find out any deviations. The good thing is here, such a wind park consists out of between 50 and 100 of the windmills. And this means you can always compare because water depth is almost the same and the structures are the same, conditions are the same. So this is a very, very interesting thing to use for also AI. It is not AI. These are parameters and things we identified already before, and we have our routines that we called algorithms before, and AI is not nothing else than such an algorithm. So what comes out from that is we have done a lot of instrumentation of these of the windmills, where you can put the sensors, if you see on the right side, before they come to before they become offshore, and then all the construction stages can also be already recorded. Currently, there are more than 800 of these structures already instrumented with interesting data. Unfortunately, they are not freely available. Another interesting case also on more or less cable monitoring was a drilling unit in the Caspian Sea in Iran. And people were aware that, if they have 8 mooring lines means that they are anchoring this structure during operation. You can see that it is not perfectly horizontal, and the Caspian Sea is not does not have too many high tides, but it is still interesting to get the information how these cables are acting, and to have an active mooring system. So what we did there was we identified how the system works and then calibrated it. And finally, more or less, platforms are the interesting thing, because some of the platforms are inhabited. Not this one. This is the Alpha Ventus. This was one of the experimental platforms in the North Sea from Germany. But on the big platforms like this here, there is a hotel on there with about 60 rooms. So this is a huge structure. And it takes the record from 80 of the windmills, then converts into certain currencies, and then transport the electricity to site. The dimensions are enormous. What we found there was on one of these platforms where people complained about seasickness. So this means the platform is vibrating in a mode which is uncomfortable. Then we were asked to monitor. We've put the permanent monitoring there, and what you see on this graph here is the records look quite good. The spikes you get is, there is so much electricity around there, you cannot really protect it 100%. But when you look at the spectrum, these lines here this is first vertical, and then we have horizontal in 2 directions. These are the computed frequencies, and what you see here, these are the measured frequencies. This is, I have never seen a difference like this in any other cases. So you know, people said, okay, we have to find out, send down divers to the structure. The structure consists of 6 vertical piles on which a jacket is sitting. Here on this picture, you see this is part of the piles, and this is the jacket. Huge steel structures. There is unfortunately no video of that, but several photos, and we could see that here this thing was moving about 6 centimeters related to each other. It was not a design mistake. The design was okay, but in the execution, something went wrong, and the fixation that should have been there was not there. This has led to the situation that you get, you know, this would be the platform. This is the structure which goes from the platform to the seabed. And then you have the piles below. This is the mud line, the brown thing, about 30 meters water depth. And we have to consider a scour, of course. You know, in the North Sea, currents are very heavy because of the tides there. And when you look at the fixation, which should have been there here, then you see that there's a buckling length for these piles of that one. I don't want to go into the figures, about 19 centimeter. But finally, it turned out that the fixation was only here, no fixation down there, and you get a buckling length of 60 meters. And well, yeah, this is not trivial anymore. And in the end, you know from Eurocode to how to drill, how to treat buckling, and it is a very, very uncomfortable buckling case you get, and the structure was theoretically not safe anymore. It has been mitigated in the end. This was the performance, the desired performance, and this was the actual performance measured out there. So you know, it really went wrong, and finally it was shifted from here to here, and there are interesting records during the mitigation process. So this is one of the best examples we have made for ambient vibration monitoring, and right now all the platforms there are fully instrumented to find out if something like this happens. So finally, in summary, so the ambient vibration method is mature, and it is applied worldwide and commercially. So this means it is not just done for fun or for scientific work from universities. But what has been learned by the industry was that monitoring alone produces just data, and you know, this data means nothing. You have to have, after that, system identification, and this has to be simple enough that operators, who in many cases are not engineers, can understand when they have to call the engineer. And finally, to combine it with a risk management. So this means somebody has to find out or give it by a threshold whether things is going in a very dangerous situation. I told you already there is very, very limited application of AI yet. So this means there is a wide field of science and development work to be done to make it fit for the applications. And well, interdisciplinary engineering is required, which is still a problem. You know, you have to do all the disciplines of engineering into one pot to find out the right solution. Anyhow, I think there's almost no problem that cannot be solved by ambient vibration monitoring. And when you have detected the problem, you know, then you normally get enough money to do some very dense sensor network, and then find out where is it, how big is it, and what to do. Thank you for your attention. I'm open for questions.
Thank you very much, Professor. We have two questions for the moment. We have Giancarlo Costa, who is writing, "Good afternoon, Professor Wenzel. Thank you very much for the presentation. I have a question regarding the storage of SHM data in bridge management. Given that raw sensor data can be quite cumbersome, according to your experience, how much of the collected data from SHM should we store? Do you find it more convenient to store raw data or extracted features, such as natural frequencies and more shapes? What is your preferred approach to data management? Thank you in advance."
Okay.
Thank you very much in advance. Yes.
Yeah. This is a very clear question. 20 years ago, where storage was difficult and expensive, we stored results more or less, which we regret now because now we know much more than before, and with the new methodologies and with the raw data, we would be able to do some much better work. So in current projects, I would suggest that you always store raw data. First of all, you can have then some routines running on the raw data that you find out which are those that tell you the most. And then in the big projects like Osman Ghazi, for example, we have a storage of 15 terabyte, and this is on a rotating process. So this means we keep the raw data for at least 1 year, 100%, then analyze it and we'll filter it, let's say, down to 5%, which is permanently recorded. This is on structures which will live, let's say, 100 years, important that you create a performance in time-wise, then, and you need the old data to do it in the same way. So currently, if you can, please use raw data. And of course, you can store the results, and every event you have to store anyway. But for permanent monitoring, just to see if something is changing, this raw data are important.
Thank you very much. We have two questions that are about other monitoring approaches. Let's say we have Riccardo Liuzzo that is asking, since bridges are typically large infrastructures, how could INSAR be implemented as a complementary monitoring technique in this way? Satellite INSAR, I guess.
Well, satellite INSAR,
it's a technique for bridge displacement.
Yeah, I know.
Okay.
We have done this in several of these research projects we have conducted. It is extremely interesting for us, but not in terms of permanent monitoring. What we did set are hazard studies. So this means by INSAR we identify active faults. We can look into the soil for some distance and find out if there is anything disturbing, which is then coming into the load specification, for example, or into all these hazard load cases. So whenever you have a chance to do a hazard study, do it and use INSAR to get your particular the seismic influences, but not only. There are other satellite means you can use where you find out, for example, landslide risks and such things, which is where an INSAR also could help, but there it is very often useful have a good terrain model and to have some, let's say, well, some images from history where you see what has happened. You know, this for the big projects, this is very, very, very helpful. So I see a good potential in what satellite images can give us.
And then we have Tommaso that is saying, thank you for the interesting presentation. And what do you think about the usage of vision-based vibrational techniques, for instance, by using camera to track cables vibrating? Thank you. So another.
Well, yeah, also first of all, you know, on every big project, you should have cameras. But these cameras will, let's say, 99% help you to see what kind of stupid things happen on your structure and how things are reacting. But when there is an incident like the incident I have shown on the suspension bridge, you know, the analysis of the visual records from the cameras was fantastic, and it is still, I would say that there is not too much good software available that helps you to, you know, the thing is very often to calibrate it in time and such things. This is not so easy, but now there is quite a lot to do to use that, and I'm sure that this will be of very much help in future. So it is also, you know, it is not able to detect what ambient vibration by a seismic sensor can do. This is no question. There are 2 dimensions of magnitude difference, but particular cables are very often vibrating visually quite well, and you can identify what's going on. And from the visions, you can also, you don't need many sensors. You can also find out what the modes are and how they look like.
Sure, very, very interesting approach. We also have a question by Monsen Redvani Alile, who is saying, you mentioned that interdisciplinary engineering is necessary. Can you provide more details about this? Thank you very much.
Well, you know, what we find, or which was a big problem at the beginning of monitoring, was that people who made sensors and who installed sensors were doing monitoring. So, you know, they are usually no civil engineers. They are mechanical engineers and electrical engineers and IT engineers. And they just provided sensors on the structure, connected it to a record system, and then went away. But you know, and these records are very difficult to analyze and understand. So this means you have to collaborate with somebody who's a structural engineer, who knows how the performance of the structure should look like, and then is able to combine the things you get from the monitoring with your theoretical finite element models, which you normally have, and then also to combine this with people of the operation of a structure, because many of these things are going back to, let's say, a mismatch in operation. We have seen these heavy overloaded trucks, for example, or other things, because we sometimes see in the records a very strange signal of a hangar, and then we got from the camera, for example, a record where we can see that there was a plank from a truck that was passing very fast, was flying away and hitting the cable. So to give an explanation why such strange records happen, it is very good that everybody is collaborating. Unfortunately, there are not too many engineers which are so multidisciplinary. Usually everybody has it is a very narrow field, has its expertise, and cannot find this the impact on the issues left and right.
Thank you very much. We have another question. So I guess this is a very interesting topic. Erai Temur is asking, which is your experience with real-time structural health monitoring? Do you implement any warming systems based on vibration data?
Well,
I guess that you have experience on that. Maybe you can tell us something more about the warning systems, how they work.
Well, you know, this is, yeah, there are many things involved here, but we are doing this since 25 years, more or less, or from almost 30 years. We still have the records and we still have the results. And if we have specifically on road bridges of medium size, we have seen that the resistance or the better performance of the structure compared to the design is in the range of 25 to 28%. So this means our structures can take more, and it can be helpful, specifically when you have a structure from the 1960s, for example. At that time in our code, the truck was 25 tons and not more. Now, according to Eurocode, we have 38 and can use 44 tons, and the gigaliners have 60 tons. So this means many of the structures where the theoretical, by the computation says it is overloaded, we can still say after we have done the monitoring that it can carry this load. So this is quite good news. But it does not mean that we have not found some structures where it was the opposite. But it is a very small minority where we have found that the structure is not fit. I don't know if this answers the question, but I guess it goes in this direction.
Yeah, maybe I guess warning systems can be useful also in case of I don't know, natural events that we don't expect, like earthquakes or big storm, so that you can have an idea about the state of the structure after the event. So maybe that's
Yeah.
an
Well,
interesting application.
I have been involved in many very big structures, and all of them are monitored more or less, somehow. And well, the very big structures are usually very robust. If there is not a major mistake in design, which we have seen on bridges, or the main reason for failing is that there is problem with construction and that people are not able to implement the design. But the very big structures are safe, let's say. Medium structures have a good capacity, but usually have some local problematic areas. But they are not very easy to be classified. You have to find out. And the main problem we have are the smaller structures. In the smaller structures, when it is a big difference whether your truck is 25 tons or 60 tons. And also, for smaller structures, let's say the checking procedures and all the construction process is not so well organized, and it is quite easy to do something wrong. We have seen it also depends sometimes on politics. When the bridge that has collapsed in Germany, for example, was made in the former DDR. So, and this at that time, the checking procedures were not as we have now, and this means this brings in deficiencies you cannot see, but that can be deadly. So this is This is again a very wide field where you can have problems or do not have problems.
I think that we don't have more questions. So maybe we can wrap up. Thank you again to Professor Wenzel, and thank you also to all participants for the nice questions and for your active participation. And we invite you to join the next EVACES webinar, which will be announced soon on our channels. And thank you again and goodbye.
Okay.
Thank you again, Professor Wenzel.
Yeah. Okay. Goodbye. It was a pleasure.
Bye-bye.
Bye-bye.